I have to say, I am really happy that we are going to wrap up this conference with Ray Kurzweil. And if any of you have not heard him speak before, you're in for a treat. I remember in the early part of this decade when most of the world was in a very funky mentality in technology in particular, I did a long interview with Ray, which honestly, I almost had to stay seated after I'd talked to him in person before, but it was a long phone call, and I just was almost literally dazed after I got off the phone. The things he was saying were so mind-boggling, and he has continued to say such things and write such things. At that point, he'd already written his book, The Age of Spiritual Machines. He's later written a bunch of other really influential books. I mean, the singularity is near amazing. I have a list here of things that he developed or has, the initial patent on. It's amazing. The first CCD flatbed scanner, first omni-font optical character recognition, first print-to-speech reading machine for the blind, first text-to-speech synthesizer, first music synthesizer capable of recreating the grand piano and other orchestral instruments, first commercially marketed large vocabulary speech recognition. So he's an inventor, an innovator, a philosopher, an author. He's going to be here interviewed. First, he's going to do a presentation, which is something we haven't let much of anybody else do with slides, but he is awesome. And then he's going to be in conversation with Susan Hassler and with you all. Susan Hassler is editor-in-chief of the IEEE Spectrum magazine, and she's been a tech journalist and science journalist for many years. So please welcome Ray Kurzweil and Susan Hassler.
Thanks, David.
Well, it's great to be here. I just spoke at Intel, and I asked the audience, does anybody recognize this tie? And they're all like, well, of course we recognize the tie. And I said, all right, what year did I get it? And they all shouted out, 93. It's a Pentium chip, photomicrograph. And that's when the web started to take off. And being the closing session, I'd like to expand our purview a little bit. In fact, even earlier than 93, talk about the last 1,000 years of the development of technology, which is going to be hard to do in 25 minutes. I think it would take me at least 30 minutes, but we'll leave out a few details. The key issue that I'd like to share with you, a key insight, is that information technology grows exponentially and very predictably. As David mentioned, I fashioned myself an inventor. I decided I would be an inventor when I was 5. And I realized pretty quickly, about 30 years ago, that the key to being successful is timing. Almost every inventor gets his gadgets to work. Most inventors fail because the timing is wrong. The enabling factors are not in place when they're needed. You have to be in the right place at the right time with the right idea. And realizing that, I began to be an ardent student of technology trends. And being an engineer, I gathered a lot of data. I now have a team of 10 people, and we gather data in many different fields and try to build mathematical models. And if a technology is not an information technology, then it grows in a linear manner and not actually a very predictable manner. But once it becomes an information technology, it grows in an exquisitely predictable and exponential manner. Now, people sometimes think this exponential growth, which I call the law of accelerating returns, is synonymous with Moore's law. But Moore's law is really just one example of many of this phenomenon. Now, as examples go, it's a pretty good one. But the exponential growth of computation, for example, the number of MIPS you can get per dollar, has been growing in an exponential manner decades before Gordon Moore was even born. And Moore's law, which is the shrinking of feature sizes on an integrated circuit, was the fifth, not the first, paradigm to bring exponential growth to computing. And I'll show you that. There's been trillions-fold increase in the price performance of computing over the last 110 years since the 1890 census. When I was a student at MIT, we all shared a computer. It took up half a building, cost tens of millions of dollars. The computer in your cell phone today is 1,000,000 times cheaper. It's 1,000 times more powerful. That's a billion-fold increase in the amount of computation per dollar since I was an undergraduate. And we'll do it again in the next 25 years. And what used to fit in a building now fits in your pocket. What now fits in your pocket will fit in a blood cell because we're shrinking the key feature sizes of technology at an exponential rate, a factor of 100 in 3D volume per decade. and that's also very predictable. Now, the common wisdom is you can't predict the future, and that's true for specific companies, specific paradigms. But if you were to ask me what will the cost of MIPS of computing be in 2012, or the cost of sequencing a base pair of DNA in 2014, or the spatial resolution of brain scanning in 2016, I can give you a figure. It's likely to be correct, because these kinds of measures, underlying measures of information technology, follow exquisitely predictable trajectories. And the trajectory is exponential. And even that rate is speeding up. We doubled the price performance of computing every 3 years in 1900, every 2 years in 1950, every 1 year in the year 2000. It's now down to 11 months. And it's an exquisitely smooth and predictable curve. And it's gone through thick and thin, through war and peace, through boom times and recessions, through the Great Depression. It's continuing now through this particular recession. So I'd like to show you just how pervasive this is and how predictable it is. And it also affects many more areas other than just computation. Health and medicine, for example, was not an information technology up until just recently. We didn't have the software that life runs on. But now that we have the genome, oh, and by the way, that was an exponential progression. We doubled the amount of genetic data we sequenced every year. So when we started the project, it was not a mainstream project. It was a renegade project. Mainstream skeptics said, there's no way you're going to do this in 15 years. We just had our best PhD students, our most advanced equipment, and around the world we collected 1/10,000th of the genome. This is going to take centuries. Halfway through the project, the skeptics were still going strong, saying, I told you this wasn't going to work. I mean, you're halfway through the project. You finished 1% of the project. But that's actually right on schedule for an exponential progression. You start out doubling little numbers. By the time you get to 1%, you're only 7 doublings away from 100%. It continued to double. The project was finished 7 years later, a year ahead of schedule, and we've continued to gear up every other aspect of biology at an exponential pace. We now have the software that life runs on, and it's outdated software. I mean, how long do you go without updating the software on your cell phone? It updates itself every few days, but these programs have not been updated in tens of thousands of years. The fat insulin receptor gene, for example, says hold on to every calorie, which was a good idea 1,000 years ago. It underlies an epidemic of obesity today. That gene was turned off in animal experiments near where I work at the Joslin Diabetes Center. These animals ate ravenously and remained slim and didn't get diabetes and get heart disease. They lived 20% longer. They got the benefits of caloric restriction while doing the opposite. And there's several pharmaceutical companies rushing to bring that idea to the human market. And we can design these interventions now on computers. We can test them out on biological simulators. We have a technology now which emerged right at the time the genome was collected that can turn genes off, RNA interference. We have new forms of gene therapy that can add new genes. Health and medicine has become an information technology. Now, before that happened, which was just in the last few years, we have made a lot of progress. Human life expectancy was 37 in 1800. But now that it's an information technology, even though everything I've mentioned is in an early stage, these technologies will grow at an exponential rate. They'll continue to double in power every year. They will therefore be 1,000,000 times more powerful in 20 years. So let me show you just how pervasive this is and predictable. And exponential growth, by the way, is not intuitive. Our intuition is linear, not exponential. It's the nature of intelligence to make predictions about the future. That's what intelligence does. And when we walked through the savannah 1,000 years ago, we made a linear prediction about where that animal would be in a few seconds and what to do about it, and that worked just fine. So our intuition, which is hardwired, is linear. But the actual progression of information technology is exponential. It makes a huge difference. If I take 30 steps linearly, 1, 2, 3, 4, 5, which is our intuition, I get to 30. If I take 30 steps exponentially, which reflects the reality of information technology, 2, 4, 8, 16, I get to 1 billion. That's why the future is surprising when we look at long periods of time. I was looking at the ARPANET in the 1980s, saw it doubling every year, predicted the emergence of a World Wide Web in the mid to late 1990s, tying together hundreds of millions of people with each other and with vast information resources. And that was heavily criticized as being ridiculous when the whole defense budget could only tie together a few thousand scientists in a year. But doubling every year is multiplying by 1,000 in 10 years, and it happened right on schedule. The Genome project was heavily criticized when it was only 1% of the project. And there's many other examples of this. So the chess supercomputer is doubling in power every year, which put the crossover point where a computer could pass the human chess champion in 1998. So I predicted that in the 80s, which was heavily criticized when an average chess player could beat the best machines. Kasparov was asked about this in 93, and he scoffed at it, saying they'll never touch me. And that was understandable in 93, but they saw it past him in 97. Exponential growth is very surprising. And just to show you how ubiquitous it is, the paradigm shift rate is accelerating as a result. Things are happening more and more quickly. The first steps in technology, the wheel, stone tools, took thousands of years to evolve. The printing press was adopted in 2 centuries. The telephone reached a quarter of the US population in half a century. And the cell phone did that in 7 years. And these old, earlier 20th century technologies took decades to be adopted by a quarter of the population. The cell phone, the web, the PC did that in a few years' time. And this has continued to accelerate. Just 3 years ago, most people were not using social networks, wikis, blogs, let alone tweets. Think back 10 years ago, most people didn't use search engines. That sounds like ancient history. Imagine life without search engines. That was only a decade ago. The pace of change has continued to accelerate. I have a whole theory of evolution as to why this is the case, but the more important evidence for this is really the empirical evidence, which I'll show you in a moment. But this is a double logarithmic graph. On the x-axis is how many years ago this paradigm shift took place in powers of 10. On the y-axis is how long it took for that paradigm shift to occur in powers of 10. And the reason that an evolutionary process accelerates is because it evolves a capability and then adopts that capability, so the next stage goes more quickly, and the products of the next stage grow in an exponential manner. So the very first paradigm shift, DNA, an information backbone for biology, took 1 billion years, but then evolution adopted it. The Cambrian explosion went 100 times faster. Biological evolution kept accelerating. Homo sapiens evolved in only a few 100,000 years, really a blink of an eye in biological evolutionary terms. And then technology emerged smoothly from the evolutionary process that gave rise to the technology creating species, and we've always used the latest technology to create the next. So one criticism of this graph is that Kurzweil only put paradigms on this graph if it fit on the straight line. If I had a paradigm that didn't fit on the straight line, I didn't bother to include it. So to address that, I took 15 different lists from 15 different thinkers and reference works, and there is some disagreement, but there's a very clear trend line. Not much happened in 1 million years, 1 billion years ago. Not much happened in 1,000 years, 1 million years ago, and so on. And another criticism of my thesis is that, well, Kurzweil takes these exponentials and just projects them out, and we all know exponential growth can't go on forever. You have 2 rabbits in Australia, you get 4 rabbits, 8 rabbits, 16 rabbits, but finally that stops when they eat up all the foliage. And indeed, we see that for information paradigms as well. There were shrinking vacuum tubes in the 1950s. That was the 3rd paradigm to bring exponential growth to computing. They finally got to a point where they couldn't shrink the vacuum tubes anymore and keep the vacuum. That was the end of the exponential, that was the end of the shrinking of vacuum tubes, but it was not the end of the exponential growth of computing. It led to research to create another paradigm. The 4th paradigm came along just in time, transistors, and finally the 5th paradigm, which is Moore's law. I mean, here's a history of computation going back to the 1890 census. This kind of shrinks the scale because every level on this graph is 10,000 times greater than the level below it. This represents trillions-fold increase through 5 different paradigms. Moore's law is just the period on the right. But what's even more remarkable than the fantastic scale of progress is look at how predictable and inexorable progression this is. We just updated this. It's a graph in my book, goes through 2002. So we updated it to 2008. I was asked, aren't you nervous? Maybe it didn't follow the curve this time, but I've done this a number of times. And indeed, but it is amazing to me just how predictable this is, because this is not the output of some tabletop experiment. This is not some government-mandated program. This is the result of the innovation and competition and IPOs and of millions of people around the world over a century through thick and thin and through war and peace, and we get this very predictable progression. And I don't want to dwell on these examples of electronics, but I mean, here, the price of a transistor, look at how smooth this is on this logarithmic graph from 1 transistor per dollar in 1968 to $500 million today. And as we've made them cheaper, they're better because they're smaller, therefore they're faster, and we have exponential growth in the price performance of computing. Cost of a transistor cycle has come down by half every year. That's a 50% deflation rate. And we see that in every example of electronics. And depending on what week it is, the economists will worry about inflation or deflation. And there is concern as more and more of the economy becomes information technology, and if it has a 50% deflation rate, the size of the economy, at least as measured in constant currency, will shrink. Because people aren't going to actually double their consumption of all these different forms of information technology every year. But actually, we more than double it. There's been 18% growth in every form of information technology over the last 50 years, despite the fact that you can get twice as much of it every year for the same cost. And the reason for that is, as price performance reaches certain levels, whole new applications explode on the landscape. People didn't buy iPods for $10,000, which is what it would have cost 15 years ago. And many of the innovations you've heard over the last few days, were not feasible just a few years ago, like Twitter. Magnetic data storage, I just put that up because it's not Moore's Law. This is another technology, different engineers, same progression. And DNA sequencing costs from $10 per base pair down to a small fraction of a penny today. Very smooth exponential progression. The amount of genetic data has continued to double every year. Many different ways to measure communication, bits on the internet, all doubling about every year depending on what you're measuring. And this is a graph I had in the early 80s. I had the first few points of it and projected this out to be a worldwide communication web in the mid-1990s. If you look at the same data on a linear scale, it looks like this. This is how we experienced the emergence of the web. It looked like it came out of nowhere, but you could see it coming if you looked at the exponential progression. We're shrinking technology at an exponential rate, and one of the primary applications of this now, we're actually building devices at the molecular level, are devices that will go inside the body. If I were to say someday you'll have millions of blood cell-sized devices keeping you healthy from inside, you'd say, okay, that sounds kind of futuristic. But I would point out that we already have dozens of experiments of doing that with the first generation of nano-engineered devices in animals. When scientists cured type 1 diabetes with a blood cell-sized device, 7-nanometer pores, lets insulin out in a controlled fashion. At MIT, there's a device that can detect cancer cells based on the antigens on their surface and destroy them. These are early experiments. You can put a computer in your brain today that's not blood cell size, it's pea size. It will replace the biological neurons destroyed by that disease. And the latest generation actually allows you to download new software to the computer inside your brain from outside the patient. If you look at what we can do today and realize these technologies will be 1 billion times more powerful in 25 years, and 100,000 times smaller in three-dimensional feature size, you get some idea of what will be feasible. So we will have plenty of computation as we go through the 21st century to do things like simulate the human brain. A key issue is what about the software? And we are making exponential gains in understanding the human brain as well. The spatial resolution of brain scanning is doubling every year. The amount of data we're getting is doubling every year. And we're also showing that we can turn this data into working models and simulations of the brain. There's already 25 different regions that have been modeled and simulated. This is a dozen regions of the auditory cortex that have been modeled, simulated, and tested. There's a model and simulation of the visual cortex, of the cerebellum, which is where we do some of our skill formation, like catching a fly ball. We always wondered, how does the kid do that? I mean, what she sees is the ball going up the air, and she's got to move her arm in a certain way. In order to make that connection, you have to solve a dozen simultaneous differential equations in a few seconds, and most 10-year-olds haven't taken calculus. So how does that work? The cerebellum actually does solve those equations, and we have modeled it and simulated it. Now, one of the criticisms of this thesis is, well, the brain is really too complicated to understand. The connections in the brain are of vast complexity, In fact, you had an article in Spectrum by Tom Horgan that made this point, that the brain is a vast complexity, there's 100 trillion connections, and according to Horgan, there's no rule, repetitive rule that we can use to try to understand this. And so it's equivalent to trillions of lines of code. Now, first of all, that's impossible. The design of the brain is in the genome. There's only about 50 million bytes of information after lossless compression in the genome. That's only about 500,000 bytes, equivalent to 500,000 lines of code. The design of the brain is more complex than it appears because it's a recursive probabilistic fractal. There are rules that are repeated over and over again. In the cerebellum, there's one structure that's repeated 10 billion times with some random variation. In the cerebral cortex, where we do our recursive hierarchical thinking, there's a more complex structure, but it is repeated billions of times. And we've actually, to some extent, understood this and modeled it and simulated it. There are now models and simulations of slices of the cerebral cortex. In Horgan's article, to make his case, he puts this image of the connections in the cerebral cortex and makes the point, well, you know, look at this. This is a vast complexity. We'll never be able to figure this out. But it turns out this is actually not, the picture that Horgan used is actually not a picture of the brain at all. It's a picture of a simulation of the brain that's running on an IBM supercomputer. So we have, by definition, figured this out. And this actually runs and does some early experiments doing hierarchical thinking similar to the cortex. The head of that project reported in the New York Times recently that they expect to actually have a simulation of the whole cerebral cortex within 10 years. All of this is driving economic growth, which is exponential. We've got labor productivity has increased from $30 to $130 in constant dollars over the last 45 years. The adoption of these technologies is exponential. This is e-commerce in the United States. You might wonder, wasn't there a boom and a bust in these dot-coms? That actually was a Wall Street phenomenon, not a Main Street phenomenon. Wall Street looked at the internet and said, wow, this is going to change every business model and turn it on its head, which was accurate, but the timing was wrong. Wall Street came back 3 years later, around the year 2000, and said, gee, it hasn't changed everything. It hasn't changed anything. I guess we were wrong and all the values went the other way. But meanwhile, the adoption was going on at an exponential pace. And in fact, this boom-bust psychology is an accurate harbinger of what ultimately becomes a profound transformation. It happened in the telecommunications industry, even happened in the railroads in the 19th century. And now we have dot-coms like Google. They aren't called dot-coms anymore, but they have $20 billion of real revenue. There's $2 trillion of revenue of e-commerce. Solar energy, actually now they're applying nanotechnology to solar panel design, which is a form of information technology, is growing at an exponential rate. It's been doubling every 2 years for the last 20 years, and there's only 8 doublings to go for it to meet 100% of our energy needs, and we have 10,000 times more sunlight than we need. Larry Page of Google and I just did this study for the National Academy of Engineering, and we believe the crossover is only a few years away where solar will be less expensive than fossil fuels for most areas. So let me sum up because we want to leave time for discussion. Actually, if you go back one slide. By 2029, we will have, these technologies will be millions of times more powerful than they are today. We will have reverse engineered the human brain. We'll be merging with that technology, but in a way we already have. The fact that I can take a device out of my pocket and access all of human knowledge does make me smarter. These are quite ubiquitous. Half the world has them in their pockets. Ever since we picked up a stick to reach a higher branch, we've used our tools to extend our reach. We're getting more and more intimate with these technologies. We're going to put them in our bodies and brains and make ourselves healthier. This progression here, which is a linear one, is going to go into high gear once we get to the mature phase of this biotechnology revolution where we can reprogram biology. So I'll leave it at that.
Well, thank you, Ray. Well, last night when I went back to my room, I found a card on my pillow that had, it was like a a paper fortune cookie, and it said on it a quote from Oscar Wilde that said that an idea that isn't dangerous is unworthy of being called an idea at all. And then it said the forecast for today was going to be sunny. So I don't think I got a chance really yet to just take out these, what all of this leads to. If you could just give us that, and then maybe we can start to talk.
Well, that's a great question. Technology has been a double-edged sword ever since we had stone tools and fire. We've used them for creativity and destructiveness. And people consider me an optimist, and they consider, for example, Bill Joy, who wrote that famous covered story in Wired, Why the Future Doesn't Need Me, as being a pessimist. But actually, he got his ideas about the dangers of these technologies from my book, Age of Spiritual Machines, and I've written extensively about them. If we can bring up the slides again, I'll show one slide. Can we bring those up? Well, I mean, take biotechnology. It's enabling us to reprogram biology away from heart disease, cancer, aging processes. But it could also enable us to reprogram a biological virus to be more deadly, more communicable, more stealthy. That specter exists right now in a routine bioengineering lab. You can do that. This is an op-ed article in the New York Times that Bill Joy and I wrote together, criticizing the US government for putting the genome of the 1918 flu virus on the web, which we feel is a recipe for destruction. And while I generally believe in open access to information, I don't think anyone would advocate, there's got to be some limits. No one would actually advocate putting the design of an atomic bomb on the web. And this is, we believe, equivalent. It also calls for development of a rapid response system, which I think is the right answer. Because some people call for relinquishment. Let's just not do biotechnology or nanotechnology because of their dangers. The right answer is to develop the defenses. I'm actually working with the Army to develop a rapid response system for biological viruses, similar to what we have for software viruses, which works pretty well.
Well, you know, we did do this issue that, in which we talked to, I'll use a word I heard yesterday, frenemies. We talked to your frenemies about the singularity ideas. And the interesting thing for us was we found people who would argue with you about the details. We didn't get the wholesale, this is preposterous response that we thought we might get from some of them. We got either the timetable is too short. So when you say that the singularity will be here in 2045, everybody immediately calculates whether or not they have a chance of being here when it arrives. But there's also all the details, like the details of reverse engineering the brain, the details of now that we have the sort of the alphabet of the genome, how do you get the grammar, as it were?
Well, when I wrote Age of Spiritual Machines in 1999, there were these different themes of criticism. The brain is too complicated, Moore's law is not going to go on forever, promise versus peril, software is inherently not capable of thinking, John Searle's Chinese Room. So I wrote Singularity's Near, which came out in 2004, specifically to address those criticisms. And it's useful to me when someone actually can absorb the counterpoint to their counterpoint and keep the discussion going. John Horgan's article, which is one of the key critics in that particular singularity issue spectrum, I don't think had read my book because he makes his basic thesis, the brain's too complicated, and there's no repetitive rule, which is just blatantly wrong. I mean, based on what we know about brain science, there is a repetitive rule in the cerebellum and the cerebral cortex. The cortex has a more complex rule, but it is repeated 1 billion times with some random variation. It's impossible for that not to be the case. It just is not enough room in the genome to store every single connection by any means. The actual manifestation of the brain is about 1 billion times simpler than it appears. And it is ironic, I think he chose an image in his book to show how complicated the brain is, which is in fact an image not of the brain, but of a simulation of the brain, which has therefore by definition been figured out. But I do welcome these dialogues. I think the implications of exponential growth are surprising just because, as I said, our intuition is linear, the actual manifestation, not of all technology and not of every phenomena, but of specifically the deep underlying properties of information technology does follow an exponential. That's been true of the amount of data we're getting about the brain, the scale of these simulations, and of course of computation itself.
Well, you touched on that our own abilities to predict are largely linear. And if the technology continues ahead of us, and you've talked about this just a little bit, is so we have technologies that are doubling and doubling and doubling and doubling. How do we sort of keep up with it culturally, politically, socially? Everybody here has been talking about Twitter, how it will be used, how it won't be used. Facebook. There are things you can see that retrospectively you can say, well, this is how it happened. But how can you predict that in some way?
It's actually easier to keep up with technology now than it was when I first started using computers in 1960, and there were a dozen computers in New York, and you had to be an engineer to use them.
Sure.
The technology is getting closer to us rather than us becoming closer to what we used to consider a machine was. These technologies like cell phones or social networks succeed because they enhance our innate human values of creating communities, of communicating with each other. You don't have to be an engineer to use them. You mentioned in the green room earlier how these technologies are getting easier and easier to use and friendlier and are basically enhancing what we do anyway, but overcoming certain limitations we have of being biological. That's what's unique about being humans. We go beyond our limitations. We didn't stay in the ground. We didn't stay in the planet. We didn't stay with the limitations of our biology. We're the only species that creates tools to extend our reach. Yeah, there are some animals that can fashion a stick, but it's not sophisticated enough to start its own evolutionary process of improvement.
Well, I think, do we have some questions from out? Yes, sir.
Cameron Elahian with Global Catalyst Partners. I have a question for you, sir. Being a great admirer of yours for many years, have you got any theories on if we look at the two parameters, if we say doubling and exponential growth, and roughly the other unit every year in one form or fashion on that, have you looked into if that's really the case into so many different things? It defines some sort of a recipe or some sort of formula or preordained thing for the whole universe, and if we looked at it instead of a year being 365 days, if we went and looked at, I don't know, 564 days or something, would the order be different? And instead of exponential being 2, there might be some other meaningful thing there, or is there some magic on that because of a year is roughly so much?
Well, the doubling time depends on what you're measuring. Doubling time for solar energy has been 2 years. Computing's down to 11 months. Human knowledge measured certain ways is doubling every 14 months. So there's nothing magical about a year. I do have a mathematical treatment of why an evolutionary process, and biology is evolutionary and so is technology because it's a competitive process, why it grows in an exponential manner. Basically, it builds on its previous results. There's actually a second level of exponential growth because as the technology becomes more cost effective, we put more resources into it. I mean, there were only millions of dollars put into computation in the 1950s. There's trillions of dollars today, so that provides a second level of exponential growth. So I have a theory of this, and there's a mathematical treatment and singularities near, but that wouldn't really be very compelling if it weren't for the tremendous empirical data we have. I mean, I started tracking, I noticed this 30 years ago. I was not looking for it. It was quite surprising to me as to how smooth and predictable these progressions are. I thought it might be an erratic curve, and we might, look back and kind of squint at it and see some kind of trend, but it actually is amazingly smooth. And now I've been tracking it for 30 years, and it continues to be on these trajectories. If you look at the underlying properties, now some people say, well, gee, if it's so inexorable, why don't we just sit back and let it happen? We don't have to do very much. It's the power of these technologies, particularly the underlying ones like computation, which is the most important one, that grow in this predictable manner. But what we do with it and how we apply it and whether or not we're going to use it to overcome our our major challenges, or whether we're going to remain defenseless in the eyes of abuse of these technologies, that history has not been written yet. I mean, that's why we need to be engaged, have conferences like this one where we look at the implications of where we're going.
Thanks.
You know, it's funny, we did a survey of the IEEE fellows and to ask them about trends that they thought were going to affect all of us in the next 10 to 20 years. And two of the interesting trends that they identified, one was sort of smart interconnecting everything. They thought that this business of having distributed networks and embedded systems and sensors, and as we're already seeing, we're already kind of always on in a very primitive way, and you're attached to your devices, and when you don't have it, you feel like you've lost a limb. I can't find my BlackBerry. It's like already, and this is the very early days. They identified that, and they also talked about, and the thing that was interesting about this, because these are largely people coming out of the physical sciences and engineering, is they thought that all of the things that would happen first would happen in biology. So extending biology, this whole idea of being able to augment your mental and physical capacity, your ability to create new life, you know, use bacteriophage to make transistor components, were things that would happen sooner than some of the other things in nanotechnology.
Well, I would strongly agree with that. I'm on the board at MIT, and we just started our first new department in 39 years. Not even computer science got its own department. And it's the Department of Biological Engineering, basically applying information technology to biology. And there's this profound revolution. It's not apparent yet because it takes time for these developments to get through the development and testing pipeline, but there's over 1,000 drugs in the development pipeline to reprogram this outdated software using RNA interference and new forms of gene therapy. I'm involved with a project where we take cells out of the body, lung cells, add a gene in vitro, which doesn't trigger the immune system, replicate it a millionfold, inject it back in the body, ends up back in the lungs, and this has cured a fatal disease, pulmonary hypertension, and it's undergoing human trials. But there's 1,000 developments like that. And up until recently, before 2003, we did not have the software that life runs on. So it was hit or miss. We just find things that happen to work. This is a very profound revolution. We have the means now, we're in the early stages, but of reprogramming biology. And it's not of infinite complexity. As I said, and I make this derivation in the book, there's massive redundancy in the genome. ALU, for example, is repeated 300,000 times. You can compress the genome down to 50 million bytes. I mean, that's the level of complexity, which is not simple. It's complicated, but it's a level of complexity that we are capable of handling.
Any other questions out there?
Is that a question?
Yes, John Romano. What will be the catalyst for the widespread adoption of solar energy? I know government's going to try and do it, but what do you see happening in the private sector over the next 5 to 10 years?
Well, there's billions of dollars of investment capital going into it, and it's not just because people are thinking green. It's because they see that the cost is coming down rapidly as we're applying increasingly sophisticated nanotechnology to new materials and new devices. I had that chart briefly there. You can see the cost is coming down rapidly. It's only a few years away from reaching parity and then going beyond it compared to coal and oil. As a result, the amount of solar energy is doubling every 2 years, but ultimately it'll be very inexpensive. So what's motivating it is economics. We spend $2 trillion a year worldwide on energy, and ultimately we can do that less expensively with solar. Now, it has a side effect that it's environmentally much friendlier. You might say, well, is there really enough sunlight to go around? There's 10,000 times more than we need. We only have to capture 1 part in 10,000 of the sunlight that hits the Earth to meet 100% of our energy needs. There's also new developments in energy storage to deal with the intermittency of solar energy. Larry Page and I did this whole study for the National Academy of Engineering on this issue. We looked at all the different emerging technologies and chose solar as having the most headroom. But there's also attractive trends in some of the other emerging decentralized renewable energy sources.
This is Philip Pieper. what's always fascinating is to hear you speak about sort of the brain and when the processing power and form factor that the brain is going to have in a couple of years is able to sort of process the same capacity as we do as a human. Do you really think that consciousness and memories are also going to be downloadable into a new device that is going to be sort of that brain? And if yes, walk us through your imagination what society is going to look like if you can reproduce yourself. And you know, there's going to be a large wish for living for eternity, not only to travel to Mars, but actually to live on this Earth. Is reproduction then just going to be a stimulus?
Well, we have to take this step by step. We will have the means of putting these microscopic-sized devices, blood cell-sized devices that are nano-engineered in the bloodstream. As I mentioned, there's already 50 experiments of doing that in animals with a range of therapeutic applications, so it's not as far out as it sounds. We'll be doing that routinely in 20 years for therapeutic functions. We'll also send them inside the brain, and they'll basically form neural implants non-invasively. We already have a dozen different neural implants that you can put in your brain that today require surgery because they're not blood cell size, they're pea-sized, like neural implant that replaces the biological neurons destroyed by Parkinson's disease. But you can actually download new software to these neural implants today. There was an article in the New York Times last week about concerns with hacking into that software that you download into your brain today. This is not futuristic because the latest generation of the software is actually quite sophisticated. We ultimately will send these non-invasively. We will do things like augment our memory and our pattern recognition capabilities, provide full immersion virtual reality from within the nervous system and applications like that. Once non-biological intelligence gets a foothold in our brains, it will expand over time in this exponential manner, not because it's self-replicating, but just because that's the nature of computational technology. So it'll continue to grow in an exponential manner. Our biological intelligence, although there's a lot of plasticity, its capacity and overall architecture is fixed. So we'll get to a point where most of the action in our brain is non-biological. It'll be on the internet. We'll be doing some of our thinking out on the cloud, which itself will become much more sophisticated. That part of our intelligence you'll be able to back up, download new memories into. We do that routinely today. I mean, in my cell phone, I download new software. I back it up. We take that for granted. If I smash it and the hardware disintegrates, the software doesn't die with it. There is information in our brains. There's a mind file. It's information that reflects our personality, our skills, and so on. Right now, that's inexorably tied up with the hardware. When the hardware crashes, the software dies with it. At least the non-biological portion of our intelligence, we will routinely back it up because that's what we do with our machines. So that's where we're headed. Now, is that just a computer that's just like this computer, but it happens to be in my body and brain? And some people have them already in their bodies and brains, which is a convenient place to put it, but it's really not me. I mean, is this me? Well, some people might consider it part of themselves, but is the real me biological, and whatever stuff I put inside me is just, not me? These are philosophical issues. We could spend a whole nother conference, and there are indeed conferences that talk about these issues. But, I have talked to people that have these computers in their brains, like Parkinson's patients. And you talk to different people, you get different answers, but almost uniformly, they will say, absolutely, it's me. And they're very proud of this new part of themselves because it has enhanced their capability compared to before when they got it.
Is there a question back there?
Lynn Wells, I've heard people begin to talk about the combination of bio and nano together as being a molecular age, as opposed to an information age. Does that resonate with you?
Well, we are going to merge these technologies. There's three sort of grand revolutions that sometimes go by the letters G and R. G for genetics, which is the biotechnology revolution, N for nanotechnology, and R stands for robotics. It really refers to artificial intelligence. And they're all intertwined with each other. They're all overlapping. They're all sort of galvanized and driven forward by advances in computation. We can use biology as an understanding, as a set of methods to create nano-engineered devices and also artificial intelligence. My vision of what we're doing with brain reverse engineering is not just modeling the brain, simulating it, and then we're just going to copy it without any thoughtful reflection. We're going to be adding to our toolkit of methods. We're going to gain some insight as to how intelligence works, and then we're going to amplify it, redesign it. That's what engineering does. We took a subtle scientific insight, Bernoulli's principle, which talks about air pressure over curved surfaces, and we amplified it and focused on it and created the whole world of aviation. That's what we're going to do as we gain these insights from brain reverse engineering. We're going to understand some key insights. How does the brain do its auto-associative recall? How does it do its hierarchical recursive thinking, which underlies human language? Once we understand that, and we are actually gaining some insights into that now, we will be able to use those insights and expand our toolkit in artificial intelligence. And we'll be building computational devices inspired by biology, using nanotechnology. So there will be a mixture of all these approaches.
Tom Knight from your alma mater has said that biology is the nanotechnology that works.
It is the example that gives us confidence that we can do that. I mean, the ribosome, for example, is a little machine, and it takes a code, a digital code on the DNA and RNA, well, actually RNA, and then builds a linear sequence of amino acids, drawing them from a stockpile. It's a little factory built at the molecular level. So it shows that nanotechnology is feasible. And in fact, we're going to use biologically inspired methods drawn from looking at how biology does these things to build our nano devices.
We have one there.
Do you look at these patterns as generating from human behavior, or do you look at these patterns as this is like gravity, this is something in the universe? Where do you see the source of these things coming from, that life moves in these patterns? Are we projecting upon it? Are they coming from within?
Well, my thesis is a theory of evolution, of an evolutionary process. We can actually simulate evolution in a computer with genetic algorithms, and it's a method that we use to actually generate intelligent designs, and we use them in some of our work. And we can see the same phenomena of a certain pattern being evolved, and then that pattern solidifies, and then it builds on that to create another pattern, and then that next step goes more quickly because it has the benefit of the first evolutionary step to take advantage of. That happened in biological evolution. So this acceleration happened before Homo sapiens even evolved. But technology is an evolutionary process. There's enough people involved that whereas each project is unpredictable, the overall result has certain predictable properties. And we see other examples in science of that. Thermodynamics talks about the properties of a gas and will predict what the gas will do. And it models every single particle as following a random walk. So it basically starts out saying, you can't predict where this particle will be. It's completely unpredictable where it'll be in 10 seconds. Nonetheless, the whole gas has very predictable properties according to the laws of thermodynamics. So this is a similar insight into these evolutionary processes. And the one we care about is technology.
But cognitive intelligence is clearly moving some of this forward. So doesn't that make a difference between the evolution of a plant and the evolution of human behavior?
This we may have to finish after the session, I'm sorry to say, because we're out of time. David, did you have a question? Or?
But I don't have a mic. Thank you. I just wanted to ask about a little bit of the economic implications. You know, you had one data point which you went over pretty quickly about labor productivity, which I believe is not universally agreed upon, that it has been moving as steadily as you argued. But, you know, one would certainly be able to say, to the degree, if you accept all these arguments, that this is not factored into the normal expectations about economic growth and social progress. And I'd just like to hear you talk about that. And does it make you, as an investor, for example, to the degree you may be one, more aggressive, more optimistic? Does it affect your thinking about those matters, just from your own wealth accumulation standpoint?
Well, it's a broad question. Let me say, first of all, that measures of productivity and economic growth factor out the whole implication of the law of accelerating returns. So when we measure the size of the economy, we still measure a dollar of computing as worth a dollar. Yet a dollar of computing today is 1 billion times more powerful than it was when I was an undergraduate. So it would have taken $1 billion then to equal $1 today. But we factor that out when we talk about the implications of economic growth. There's no question that this technology makes us more productive. Nobody could do their work today, and I'm talking about anyone, musicians, libraries, graphic artists, journalists, without the tremendous power of the tools that we have. And it's also harnessing our human biological brain power better by harnessing us in social networks, the whole phenomena of the wisdom of crowds, as opposed to the wisdom of lynch mobs, and the ability to find people with whom you can add your intelligence to theirs throughout the world to create communities based on common interest is a very powerful phenomena. It's very democratizing. I wrote in my first book in the 1980s that the Soviet Union would be swept away by the then emerging decentralized electronic communication, and that's what we saw in that 1991 coup against Gorbachev. The rise of the web led to a tremendous wave of democracies, and we see it profoundly now as a player on the world stage in recent events. And it's also democratizing in terms of the tools of productivity. I couldn't help but think during some of the earlier presentations how, say, take movies. A kid in her dorm room can create a full-length, high-definition motion picture in a dorm room with a $500 camera and her PC, and are doing that and creating very convincing, high-quality works. A couple of kids at Stanford, created Google on their $1,000 laptops. A couple of kids at Harvard created Facebook with their $1,000 laptops. These tools are in everybody's hands. So you don't have to be influential or have access to a Hollywood studio or a big corporate lab in order to do this kind of disruptive thinking. In terms of economic growth, first of all, this growth of the power of information technology is continuing during the current economic downturn, completely unabated, as it did during the Great Depression or any other recession we've had. It does increase the power of the tools we have to be disruptive. Information technology has grown 18% in constant dollars over the last 45 years. I mean, that is not controversial. So that is where a lot, I would say all of the economic growth is, or virtually all of it, but certainly everyone would agree a lot of the economic growth is coming from that. And information technology is of vast proportions. I mean, you go back to the 1950s and you can measure it in millions of dollars. So these disruptions will continue. It's very hard to predict, though, which organization is going to be the next Facebook or Twitter or Google. But they're going to keep happening at an accelerating pace.
Thank you. Thank you very much, Ray, for this really fascinating conversation.